What's up guys, welcome back to the next video. Guess what we're going to talk about today? Assembly language, that's right. We're going to learn how to add numbers, 16-bit numbers in assembly language. And then as an added bonus, we're going to show you how to use that assembly language / machine language program in BASIC. So before we get started with the code, let's do a quick review of how the computers, specifically the Atari 8-bit line of computers, adds numbers in memory using binary math. We're also going to understand how the carry flag works, and then we're going to get into the code and we're going to see how this works in assembly language. So break out your Atari Assembler Editor cartridge and let's get started. So let's go ahead and review basic binary addition, and to start off with, we're only going to use 4 bits. So let's go ahead and add the numbers 8 plus 10 in binary. Now the number 8 in binary is 1, 0, 0, 0, and the number 10 is 1, 0, 1, 0. So when we add binary numbers, we add starting from the right, column to column, and we carry over any digits that are necessary as we do the add. So we're going to add 0 plus 0, which is the rightmost bit, and of course that's going to add up to 0 because in binary 0 plus 0 is 0. The next column we're going to add is 0 plus a 1, and in binary 0 plus 1 equals 1. We move to the next column, the third column or the third bit, and we add 0 plus 0, and that of course equals 0. Now let's watch what happens in the fourth bit. 1 plus 1 in binary is 1, 0. So obviously we've got to write the 0 down, and we have the extra carry bit on the side. The carry bit is very important. Our final result is 1, 0, 0, 1, 0 in binary, or 18 in decimal. You can check this using your programmer's calculator. Let's go ahead and continue, and let's go ahead and do a full 8 bits. Let's take a look at what it takes to add the full 8 bits. It's basically the same process. So let's go ahead and add the number 255 plus 1, which will obviously bring us into an overflow or a carry situation, 256. So 255 is 1, 1, 1, 1, 1, 1, 1, 1. And the number 1 is 0, 0, 0, 0, 0, 0, 0, 1. Let's go ahead and add these columns, starting with the rightmost bit, which would be the 1 plus the 1, which is obviously going to give us a 1, 0. So we write down the 0, and then what we have to do is always remember to carry the 1 into the next column, which would be bit number 2. And so 1 plus 1 is again 2 in binary, which is 1, 0. So I think you can kind of see the pattern that's going to develop here. We continue to add the 8 digits, and what we end up with is the carry bit at the end. So what we're going to end up with is 1, 0, 0, 0, 0, 0, 0, 0, 0. And of course that in decimal equals 256. Now let's look at another important piece of information that must be understood, and that is most 8-bit computers, including the Atari, store 16-bit words in memory with the low byte first and the high byte second. The Atari uses the convention of storing addresses in the least significant byte / most significant byte manner in memory. So in other words, the hex value D016 hex in memory, the 2 bytes would be reversed. The low byte would be first, the high byte would be second. So you can see here in memory location 4000 in memory, we can see the 16 is first in memory, and then at location 4001, the D0. This is called the least significant byte / most significant byte. This is important to remember, that when you're retrieving 16-bit words from the Atari's memory, you have to retrieve the low and the high byte, or the high byte first, place it in memory, place it in your variable, and then the low byte behind it. So just remember that. That's important. What's up, guys? So we're back here at the Atari, and I've got some source code loaded up here that represents the program we're going to use for our testing today and for our learning. As you can see, it's pretty short. And before I get started though, what I wanted to do was, I noticed in some of the other videos, this cobalt blue background may or may not be showing up ideally for you guys on your end watching this through YouTube. So I'm going to try something a little different today. I'm going to try changing the background color to a black color, and I'm going to make the border a cobalt blue and see if it makes it a little clearer for you guys. So the way we do that is in the graphics mode 0, which is the text mode we're in on Atari. Location 02C6, that controls the background color of the screen. So we can do a display 02C6 here in the debugger, and you see it's 94 right now, which is that cobalt, well, it's actually a light blue color. So using the command we learned in the last video, which was copy to memory, we're going to shove into 20C6 a 0. And that's going to change our background color to black. And going along with that, we can change the border color by shoving into 02C8. Let's throw 60, which I believe is cobalt blue. So I'm thinking that possibly this is going to look a little bit better on the capture device for when we're looking at code. All right. So here's our listing. This is going to allow us to take two 16-bit numbers and add them together and store them into a third number or a third location. And we'll be able to display the sum of those two numbers. So let's take a look at what we're doing here in the first few lines of code. So one of the things that we didn't talk about yet when it comes to the assembler editor is using labels, assigning to labels constant values. So we've used labels before. We used them in our last program to create a loop. But what we're going to do is we're going to take a label and we'll call it num1, and we're going to assign the value CB, which is a member location that we're going to store the first number that we're going to add. So in the code, instead of referencing CB, we can reference num1. We're going to do the same thing with num2 label. We're going to assign it memory location CE, and we're going to create a third label called sum, and we're going to assign that to D4. Okay. And as usual, we're going to set our program here at line 60 to 4000 in memory. Now line 80 is interesting. What this is going to do is it's going to clear the decimal mode for the processor. We haven't talked about binary decimal mode on the processor, but we will in a future episode. Just for now though, when you're doing any addition, if you're not working in decimal mode, we're going to clear that flag. Okay, so this is important to do, and we'll get into this a little bit later in another video when we talk about the decimal mode of the processor. All right, so let's go ahead and get down to 105. So line 105, we're going to load the accumulator with the value, immediate mode, hex value 01. So let's talk about what I'm trying to do here before we get any further. I'm trying to take 0001 and I'm trying to add to that 0005, which should end up equaling 0006. Real simple math. But one thing to understand is that when we're talking about this in the computer memory of the Atari, this 001 is actually going to look like this in memory. Okay, it's reversed. Remember we talked about this in the slides. We're talking about the lowest significant byte and then the highest significant byte. And this is what it's going to look like in the Atari. Okay, so this number is going to look like this. So we have to remember that when we're working with these values and we're trying to load values into the accumulator in immediate mode. Because the load accumulator in immediate mode will only take 1 byte. Okay, it's an 8-bit value. So we have to take the 0001 and break it into 01. And we're going to store that in the low byte of the first number. So if you think of num1 in memory, we've got CB, and then we've got CC, okay? So what that's going to look like in memory is if we had CB and we had CC, okay? CB is going to be 01, and CC is going to be 00. For the human readable format, it's going to be 0001. Everybody see that? Okay, I hope so. It's one of those things that takes practice to get used to, but once you get used to it, it's pretty simple. So we're going to load 0, 1 into the low byte of the first number, and we're going to load 0, 0 into the high byte. So what we're doing is, you can see here, we're saying stored in the num1, which is CB, remember our label, and by adding 1 to CB, we end up with a quick move to CC. Everybody see that? So num1 in memory is going to be 0, 1, 0, 0, which in human readable format is 0, 0, 0, 1. Let's take the second value that we're adding, which is 5 in immediate mode, hex mode. We're shoving that into the low byte of our second number, num2, and we are loading 0, 0 into the high byte of the second number, which is num2 plus 1. So let's just watch that happen in memory. I'm going to put right here in line 180, I'm going to put a jump to the end. And if you look in here, I've got a label that takes us to the end of the program. So what I want to do is I just want to put those two values into memory and end the program so that we can go into the debugger and look into memory and see what happened. So let's assemble this listing with our ASM command. We'll let that finish compiling or assembling. So let's go into the debugger and let's display CB, which was num1. All right, so you can see here, this is CB 0, 1, this is CC 0, 0. So in reality, human readable format, what we're looking at is 0, 0, 0, 1. So that's what we wanted. So let's look at the next location, which was it CE? Yes. So here's the second number that we're adding. So CE 0, 5 and CF 0, 0, which again in human readable format is 0, 0, 0, 5. You just got to remember that in the Atari, in the 8-bit world, you've got the low significant byte first and the most significant byte second, or the low byte first and the high byte second. Okay? So now that we have those two values in memory, oops, go back to the editor. Let's remove our jump command, which was just a label, blank label. So now let's take a look at what we're going to do next. Now, the 6502 processor has what's called a carry flag, and the carry flag gets set when you're adding two numbers together and there is a carry. So for example, adding 1 and 1 is a 2, there's no carry. But if you add FF plus 1, that takes you past the size of a byte, 256, that's going to create a carry. So we have to clear the carry before we do any addition, and you'll see why that's important in a minute here. So let's do the addition, and the way we do the addition is we have to add the low bytes together first, and then we add the high bytes together second, okay? So we're going to load into the accumulator the low byte of num1, which is num1, and we're going to add with carry, ADC, num2, which is the low byte of number 2. So in this example here, we're loading the number 1 here, and we're adding the number 5. And then what we're going to do right after that is we're going to store the result of the accumulator into sum, which is the low byte. So we're adding 1 plus 5, which is 6, and we're storing 6 into the sum. Now, we also need to take care of the high byte, just in case there's values there. Now, in our example, they're both zeros, but they may not be zeros in our next repetition. So we have to load the accumulator with the high byte of num1, which is num1 plus 1 in memory. And again, we're adding with a carry, num2 plus 1, which is the high byte of num2. And we're going to store the results of the accumulator into our sum plus 1, which is the high byte of sum. So, and then we're ending the program with a label that says end. There's no operation. All right, so let's go ahead and assemble this. And we're going to basically take a look at the results of this in memory and see if we get the outcome we're expecting. All right, so let's go into our debugger. Let's execute the program. All right, so CB should contain our 0, 1. CE should contain our 0, 5. And our sum, which is in D4, should contain our 6. And there we go. So D4 is 06 and D5 is 00. Now remember, the sum in human readable format is really right there. All right. So let's modify our program just a little bit and let's do it again. This time, let's take the numbers up a little bit. Let's add A, and we'll go ahead and add 1 to A. All right, assemble. Now A in hex, as you know, is 10, and a 1 is a 1, so we should end up with a B, which is 11. And let's just display our result, B. There we go. Everybody see how that worked? Okay. So let's test this a little more, and let's see if we can roll our sum into the high byte. In other words, we're going to produce a carry because we're going to add two values that equate to a number that's greater than 255, which is what we can store in 1 byte, and we're going to make it carry into the next binary digit, which will take us into a 16-bit number. So let's go over here just for laughs. Actually, before we do that, let's do FE as our first number, and we'll leave that at 1. FE is 254. And if we add 1, that should give us a 255, which should keep us in the 1 byte range of a result. And we are. You see here, we're still in 1 byte here, which is the low byte. The high byte is still 0, okay? So let's challenge this a little bit longer. Let's go up here and let's make this first value 255, and we're adding 1. And we know this is going to overflow and generate a carry. So let's go ahead and let that happen and see what happens into our high byte. All right, let's execute. All right, so now let's take a look at D4. Aha. See what happened here? We no longer have any value in our low byte, we just have in our high byte. So now what we ended up with is 0100, okay? Which in decimal is 256. All right. Now, let's go ahead and take a look at what happened here. All right. We added here the low byte, which was 250, which was FF 255 20 or 21, and that created a 256, which stored the sum into the value sum here, which what it ends up storing in the sum the first time around is a 00, because what we're doing is we're creating a carry, okay, which is going to carry that bit over into the carry bit, so that when we come down here and we add with carry, we're adding the high byte together with the carry. All right, and what we can actually do is we can trace through this program. So let's go into our debugger so we can talk about this carry flag and how it works. And what we're going to do is we're going to do a step trace like we learned in the last episode through our program. What this is going to allow us to do is step through the program line by line. So first thing we're going to do is we're going to clear the decimal mode in the processor. Now, first thing we're going to do here is load the accumulator with 255. Now, one flag I want you to keep in your watch is the processor status flag. As you can see right now, the value is B1. Now, I can't go into the explanation on this video as to what this hex value and how it breaks out to the 7 bits of the processor flag, but basically if you take B1 in your scientific or programmer's calculator and convert that to binary, you'll be able to see which bits are turned on. For our particular sample here that we're doing, what we care about is when the processor flag equals 33. 33 in binary equals 100001. The first bit in the 6502 processor is the carry flag. So 33 is going to signal to us that our carry flag has been set. So let's go ahead and continue. So we've loaded 255 into the accumulator, step through. We're storing 255 into memory location CB, step again. We're loading 00 into the accumulator. and we're storing that into CC. We step again. We're loading into the accumulator 0, 1. We're storing that into CE. We're loading into the accumulator 0, 0. And we're storing into the accumulator CF, or memory location CF. And now we're going to clear the carry flag. And you can see our processor status right now is 32. So from here on out is where we want to pay attention to the carry flag. Okay. So we're going to load what's in CB, which is our 255. You can see that in the accumulator value right here, FF. Okay. We're going to step through, and we're going to add with carry what's in the CE. And we know that in CE it was 0, 1. So look what happened here. We told the computer to load, or we told the computer here to add with carry what's in the accumulator, what's in CE. So we know we had in our accumulator, if we look up here, the last instruction, we had FF, and we're adding what's in CE, which is a 1, which is going to make the value 256. So look what ended up in the addition in the accumulator, a 0, 0. Well, we can't write 256 as FG. That wouldn't work. So what happens is we set the carry flag here, processor status. Remember I told you 33, 1, 0, 0, 0, 0, 1. I can tell that the carry flag has been set right here. So the computer's processor knows that we have a carry, and we're going to put in the accumulator 0, 0. Okay? Let's step again. We're going to store that value into D4, all right? Which again, that's going to be our low byte. Okay, 0, 0, going into our low byte. Let's step again. We're going to load into the accumulator what's in CC. We're going to add with carry what's in CF. And you can see now we have in our accumulator 0, 1. Okay, we didn't have a carry, by the way. Processor is 3, 0. So now we have a 1 in the accumulator. And we're going to store that in our high byte, which is D5, right here. Okay? All right. So does everybody see how that worked? So to add the two 16-bit numbers, we add the low byte from the first number to the low byte of the second number, and the high byte of the first number to the high byte of the second number. We add with a carry. The processor takes care of the addition for us as long as we clear the carry flag here before we do our addition, and we add with a carry. The processor will automatically roll that bit to the next column, if you will, and place our value in the high byte. Okay, let's try another example. Let's do, I don't know, let's do F. Oh, one important thing to note is when we're adding two 16-bit numbers on the Atari, the highest number we're going to be able to add is 65536. I don't want to put the comma there. That's the highest. Actually, it's 65535. That's the highest number that the Atari can represent as far as 16-bit numbers. If we try and add 65535, we try and add one more number to it, we'll end up with zeros all in our memory. And since this program is not taking into account anything higher than 32 bits, that extra bit will sit, the carry flag will be set, and there will be nothing to handle. So that's one little, maybe we can do a little bit in the future as far as adding some bigger numbers. But right now we can only do 16 bits with this program, okay? So if you have any questions about that program, what we've done so far, make sure you take notes and give me some comments. But what I want to do now is I want to take this program and modify it just a little bit so that we can call it from BASIC. And that way we can add numbers from BASIC, and I'll show you how we do that right now. Okay, so I've got a new program here, or I've got the old program modified slightly. You can see we're still working with the same memory locations we were before. Okay, same memory location, clearing decimal. The only thing different now is instead of hard coding the values that we're adding into the program, we're going to be receiving those numbers from our BASIC program. So we have to as we learned before, we do our first PLA. This first PLA ends up being the number of arguments, which we don't care about in our example because we know we're going to be receiving 2 arguments. And then the next pull accumulator is going to be our first argument. And the way that BASIC passes arguments to the assembly language routine is the high byte comes first of the first argument, and then the low byte of the first argument comes second, and then the high byte of the second argument comes third, and the low byte of the second argument comes fourth. So we just have to make sure you keep that in mind as we're receiving the arguments and put them in the right order in the memory. So for our example here, the first argument we're pulling is the high byte of the first argument. So we're going to store that in num1 plus 1. Remember, the most significant byte goes second in memory. The lowest significant byte goes first in memory. So the first thing I'm going to do is grab the high byte of the first argument and save that into the high byte of our first value. We're going to pull again from the accumulator, and that's going to be the low byte of the first argument, and we're going to store that in the num1. We're going to do the same thing for the second argument. We're going to pull the first argument is the high byte of the second argument, which we're going to put in num2 plus 1. We're going to pull again the fourth argument, and that's going to be the low byte of the second argument. So the only thing different here is we're pulling arguments, the numbers we're going to be adding from BASIC. Line 190, we're going to clear our carry flag, and then we're going to do our addition like we did before, where we're going to load into the accumulator the low byte of num1. We're going to add the low byte of num2 with carry, store that into our sum, low byte, and then we're going to load the high byte of num1, add with carry the high byte of num2, and store that in the high byte of our sum. So we're doing exactly what we did before, and then we're going to return to subroutine RTS, which is going to transfer control back to BASIC. All right. So let's make sure this assembles. Okay. So now let's switch out to BASIC, and I've already converted this machine language code into a format that we can use in BASIC. So let's go take a look at it in BASIC now, and let's actually call this machine language routine from BASIC, which will add 2 numbers that we pass to it. Okay, so here we are in BASIC, and what I've got here is these data statements represent that machine language program that adds 2 numbers that we modified for BASIC. And what we're going to do is we're going to loop through like we did before, and we're going to poke those values into location 4000 in the memory. So let's go ahead and run this. So now our machine language program is ready in memory. So what we can do is we can test this. We can say the sum equals user routine, and we're going to pass the memory address where our program is. That's 16384. And let's do that first example before where we added a 1 to a 5. All right. So if everything worked the way we thought it will, sum should equal 6. And it does. Awesome. Let's try adding the bigger number like we did before. 255 with 1, 256. So it works. So now you can see how easy it is to take the addition program that we just wrote and use it in BASIC. Let's clear that out so you can actually see it. All right, so there you have it. 16-bit addition in assembly language. Type the program out if you can. I'll leave a link in the description where you can actually download the source code in assembly language. Practice with it though. Get used to thinking in terms of low byte and high byte. And next we'll take a look at some subtraction, and we'll do some multiplication and division a little bit later on. But get very familiar with doing math in assembly language because it's something you're going to be doing all the time. And since we're dealing with an 8-bit processor and we're dealing with 16-bit addresses, we have to get used to dealing with low bytes and high bytes in our calculations and in memory. All right, there you go. Adding numbers in assembly language. As you can see, it's not too difficult, but it is an important concept to get down and fully understand, because as we start writing more and more advanced assembly language programs, adding, subtracting, multiplying, dividing, which we're going to get into those lessons as well, all of these are going to be very important, and you want them to become second nature so that you can focus on the core game or the core program that you're writing and not have to go back every time and try and figure out, how did I add, how did I subtract? You really want to get these basics down pat before we move forward with the advanced programming. So anyway, hope you guys learned something. Hope you enjoyed the video. Make sure you like, make sure you subscribe. Give me some feedback. Let me know if you want me to change the format, or if you want me to go in a certain direction, or if you generally just don't like, or if you do like what I'm doing. Anyway, I appreciate the views. Keep programming, and I will see you in the next video. Go Atari!